Good morning, everyone, and welcome back to the day 2 of Gyan course on in situ design and catalytic dynamics of nanomaterials for water and air quality monitoring and mitigation. So, we hope you had a thought provoking and inspiring day yesterday. And today, let me begin with another scientific quote, and that is by Carl Sagan. And what said was, science is a way of thinking much more than it is a body of knowledge. So, let us continue deep uh, into yesterday's foundation, which was laid by Professor Zain. And before we start today's talk, I'd request Dr. Raisuddin sir to kindly felicitate Professor Zain by offering a floral bouquet. So, good morning, Professor Zain. And he will be talking on a title that is Mechanism of Heterogeneous Catalysis. Over to you, sir. Thank you.
Assalamu alaikum. Today, inshallah, I hope yesterday we had good lectures and I hope we had some nice conversations. Today, inshallah, we will continue what we started yesterday and I hope it will be fruitful for any one of us. Thank you very much. Let's start. Today, inshallah, I'll talk about another topic which is adsorption. Of course, everybody knows what's adsorption. Adsorption is very important technique for water purification. I think you know that there are many techniques used for water purification, like adsorption, like photodegradation, like filtration, and several techniques. One of these most important and the easiest ways for water purification is adsorption. Let's talk about it and just this slide talk about very important and also known definitions, which is what's adsorbate and what's adsorbent, what's solute and what's solvent. The adsorbate of of course, it is a substance being adsorbed, which is either gas or something in liquid, and adsorbent, which is a material which makes adsorption or takes this fluid, which gas or liquid, to its surface. Solute, of course, solute and solvent are well known, which is bigger amount, which is lower amount. The bigger amount is solvent, and lower amount is solute. But what about what there is very important or very fundamental expression, which is sorption. Sorption means everything about taking these materials from fluids, liquid or gas, to the surface. This is sorption. But if we divide adsorption, there is absorption is some, if you take the amount of, if you take the solute or the material to the surface, this of course it is being adsorption, and if it's in the bulk it will be absorption. Like if you have a piece of a chalk in water, just it will be on the surface, this is adsorption. But if it use sponge, it will be absorption. This is fundamental. And what about the adsorption? Adsorption is divided into two parts or two types, which is physical adsorption and the chemical adsorption. Of course, we should know what is the difference between chemical adsorption and the physical adsorption. The main, of course, this is how it looks like. This is physical absorption. I think you know now, both of them, it has differences. Please let me tell you briefly what is the main difference between physical absorption and the chemical absorption. The main difference which causes all the other differences is forming a bond, chemical bond between the adsorbate or the gas and the solid. In chemical absorption, there is a chemical bond. However, in physical absorption, there is no chemical bond, just condensation of the molecules together on the surface of the solid and forms a multi-layer of these gas molecules on the surface. This means the main difference, which causes all the other differences, if you count the differences between them, 1, 2, 3, 4, 5, 6, all of them, the origin of this difference is the formation of chemical bond between gas material or fluid and the solid. And this is brief the, listing of the difference between physical absorption and the chemical absorption. The force in physical absorption, just like condensation, and in chemical absorption, it's a formation of chemical bond. Chemical bond means, I am sure you know, formation of chemical bonds is followed by releasing energy or absorption of energy. Formation of chemical bonds. Any reaction, it should have two stages of energy, absorption and desorption, release and absorption of energy, and also release of some energy. The breaking of bonds is always followed by absorption of some energy, and formation of bonds is always followed by release of some energy. In chemical absorption, there is a chemical bond is formed, and release of energy becomes after. Here is the absorption, heat of absorption. In physical absorption, it is very small because there is no chemical bond is formed. But in chemical absorption, there is a large amount of energy is released because it's a chemical bond is formed. In the number of layers for physical absorption is one or multiple layers, but in chemical absorption it's only one layer, because the formation of bond is only between the first layer and the surface. But in physical absorption it's only condensation, because if you make the first layer condensation like this in here, in this one, the first layer condensation between the molecules of the gas and the surface. However, after that, condensation between the second layer and the first layer, and the third layer is condensed on the second layer, and so on. Let's turn back here. Dependence of gas and the solid. Of course, if you make reaction, this means that the reaction depends on both reactants. Here, the gas and the surface are, please consider it as two reactants. Then it will depend on the formation of chemical absorption, will depend on both of them. However, in physical absorption, it will not depend on both of them. Okay. How fast? Of course, in physical absorption is rapid, but in chemical absorption, which is formation of chemical bond, little bit slow. In physical absorption, of course, there is condensation and evaporation, while in chemical absorption, just formation of chemical bond, and that's it, until you break this bond with some energy. And I'd like to show you with related to the formation of the chemical bond. Of course, as I just mentioned now, the formation of chemical bond should be followed by the release of some energy. This energy is the heat of absorption. This means the heat of absorption is exothermic or endothermic. It should be exothermic. Let's check if it is exothermic or endothermic. Heat of absorption is, here I want to tell you another point is, how can we determine the heat of absorption? The heat of absorption is determined by the heat of absorption is determined by heat of absorption is the evolved energy. Okay, but if we break the heat of absorption is the released amount of energy. Okay, let's check if the it is endothermic or ectothermic. Of course, you know this is delta G equals delta H minus T delta S. Of course, delta S after absorption, is it positive or negative? Should be negative. And delta G, of course, if it's a spontaneous process, then delta G will be negative as well. So delta H is negative. So delta H is a negative value because it's summation between summation of delta G negative value and delta S T delta S is a negative value. This is so it is surely exothermic reaction. How can we calculate it? Let's see. Delta G, yes, that's what we just mentioned now. Delta G is negative and delta S is negative. So we calculated by Clausius equilibrium equation, ln P2 over ln P1 equals Q, which is delta H heat of absorption divided by R. R, of course, you know, it is a universal gas constant. It has 3 values, and we will mention about it soon, inshallah. Uh, P2 at T2, P1 at T1. If we have some data, I will show you. Of course, we can replace Q by delta H, and K, the rate of absorption, with P, it's the same to have these equations. If we have an example, when hydrogen adsorption on tungsten powder with coverage of theta equals zero point 0.1, it was noted that hydrogen pressure was 3.06 kilopascal at 600 degrees C, and it was 6.6 kilopascal at 700 degrees C. Calculate the heat of absorption in this temperature range. Of course, it's very easy. It's direct calculations or compensation. Ln P2 over P1 equals Q by R, T2 minus T1 over T2 T1. Of course, you know, in thermodynamics, you should use T as Kelvin, but only you can use it in Kelvin or Celsius in subtraction only. Okay, but in multiplication or other other mathematical process, you should use it in Kelvin. In this case, we should use it in Kelvin? We will transfer 600 or make it from degree C to Kelvin, in as you can see here, and we used the R value 1.9. What will be the unit of Q? What will be the unit of Q if we use this R value equal 1.987? This means Q should be with the same unit. If we use R equals 8.2, which is joule, so Q should be in joule. And this value is in calorie mole calorie for every calorie over mole Kelvin. Then Q should be in calorie in this equation. We just substitute and make it like this. Q, we will have Q value, which is delta H equals 28.5 kilocalorie per mole. Then we could calculate the delta H in this example. And I have a little advice for you. Of course, in each exercise or in each problem you can get, it's like a small story. Just imagine we add something to something, we divide something, we took something. It's small story. So each part of this story should be useful. The writer doesn't add it just haphazard. But in this case, it will not be a problem for us if the equation we will use is ln P2 over ln P1 equals Q by R T2 minus T1 over T2 T1. Does this equation has any information about theta or not? It doesn't have any information about theta. This means we will not use this information. But we added this information, but it is for to distract you, okay? So you will not use it. So don't be distracted. Just focus on your equation and substitute these values, and you will get delta H finally. We have other problems like this. We can just forward to you, and you can try by yourself if you have, inshallah, I am sure you have the ability to solve these problems to calculate the delta H of these reactions. Any thing or any process or any phenomenon should have some factors affect this phenomenon, okay? Some things that increase absorption and the other parameters which decrease absorption. The factors affecting absorption process of gases on solids are as follows. Number one, the nature of adsorbent. Nature of adsorbent, the nature of the solid material. The solid material, what is its nature? Number one, about surface area. Of course, you know the surface area. Once the surface area is high, the absorption will increase. If surface area is low, absorption will decrease. And polarity. Polarity is a very important as well. A nature of adsorbate, like liquefaction and polarity, and temperature of the adsorption medium, the temperature, and also the pressure of the adsorbed gases. Let's take one by one as follows. For example, about surface area. Of course, the increase of surface area means increase of active sites that can make absorption, which leads to increase of absorption, the amount absorbed of the gas on the solid surface. Why? Of course, we just mentioned that the increase of surface area leads to an increase of absorbing sites. So finally, divided solids and some porous substances are good adsorbents. Why? Finally divided means if we go from bulk material to divide to nanomaterials, that means I increase the surface area, that means I increase the availability or the available sites to make adsorption. And also porosity. Porosity means the presence of some pores on the surface of the material makes it it's just not because it's porous, but because this porosity increases the surface area. Like if you remember the sponge we just showed some time before, it has a lot of pores. This means its surface area is very high. If it's just blocked everywhere, then it will have a very low surface area. Of course, if we are sitting in a hole like this, surface area will be like this. These are the sites that can accommodate students. And if it is small, but if it is very large like this, it will have much more students and absorption will be better. The other factor for nature of adsorbate is the liquefaction. Liquefaction means is the transformation of or change of gases to liquids. This is liquefaction. If liquefaction, as we mentioned before, that physical absorption is a kind of liquefaction, is a kind of van der Waals forces between the adsorbate and the adsorbent. So if the material of the gas is easily liquefied, like ammonia, HCl, Cl2, CO2, then its absorption will be higher. If it is permanent gases like oxygen, nitrogen, hydrogen, then its absorption will be very low, or its absorption will be very small, or very little. It will need very low temperature to make absorption, because when it transfers from gas to solid, this means I am trying to condensate these molecules to the surface. Condensation means liquefaction. Okay, so if the condensation of this of NH3 HCl is easy, this means its condensation is easy, liquefaction is easy, and the absorption is better. But if the other gases like oxygen, hydrogen, liquefaction is difficult, condensation is difficult, and absorption is difficult. Finally, we will talk about polarity. Polarity means the formation of charges on the surface of the adsorbate and the adsorbent. These charges make it, of course, plus is attracted to minus, minus is attracted to plus. Okay, this means the polarity makes it easy to make adsorption if they both are polar surface. And I just want to remind you that there is a very nice and fundamental in dissolving materials. They were always saying polar dissolve polar, or like dissolve like. This means polar things are attracted to each other, and the non-polar materials are attracted to each other. If you want to dissolve an aromatic material, you should go to non-polar solvents. If you want to dissolve inorganic material, which is ionic, you should go to, like NaCl, for example, you should go to water, which is polar. But if you take this NaCl to, for example, diesel or petrol, like benzene, it will not dissolve. And I think there is a very nice quote in Arabic in that الطيور على أشكالها تقع, that the birds are going to its similar. It is the same meaning. The final is the concentration or the pressure of the gas, concentration of solution of solute in solution, and the pressure of the gas. If this concentration is high, the absorption will be high, and vice versa until saturation. This is how the pressure goes. At very low pressure, or an increase in the pressure leads to an increase in the amount adsorbed. More increase leads to increase of the amount adsorbed until the rate will be lower, and then a parabola or saturation will occur at the end. And the second is temperature, and the third is temperature. We adsorbate and the adsorbent and the temperature. Temperature, of course, it is, as we mentioned several times yesterday and today, it's a product of the reaction or a reactant. Temperature, if we increase temperature, what will happen? If we have condensation, for example, of nitrogen, NH3 over a solid, what will happen? If we increase temperature, will NH3 will be dissolved or not? It will be dissolved or not? It will not be dissolved. This means increasing the temperature will lead to decrease the amount adsorbed of the fluid on the solid surface. And this is very simple example that if we have nitrogen at 273, which is 0, only 10 centimeter is absorbed of nitrogen on the solid. And if we decrease temperature, the amount absorbed will be higher, and so on. And if we decrease temperature more, the amount absorbed will be higher. And this is a very simple graph showing that the amount dissorbed adsorbed decrease by increasing the temperature. Of course, this is a small or minute explanation why decreasing the temperature leads to increasing the amount absorbed and vice versa, because absorption is exothermic, and if we add temperature, this means it will go to the other direction, according to Le Chatelier. And this is a very simple experiment that we add adsorbate on, we add gas on a decrease with it increases increased temperature. This when we add the material at 0 degrees C, its amount adsorbed very high, and if we increase temperature, the amount adsorbed becomes lower and lower and lower after increasing the temperature. Effect of polarity of solvent and adsorbate. The polarity is very important as well, because there is also another very nice experiment. We took butyric acid, propionic acid, and acetic acid. All of these are aliphatic acids which has different molecular weights. If we add these acids to different solids and the different solvents, we can see the experiment. It will be like this. Adding aliphatic acids to toluene solvent. Toluene is nonpolar over silica. The acetic acid will be easier to be absorbed and higher absorption because it is the lowest molecular weight. But in case of using water as solvent, which is polar, over carbon, which is non-polar, the butyric acid higher molecular weight will be better in absorption. So absorption depends on the surface polarity and the surface and also the solvent and the molecular weight, because the polarity affects very much in absorption process. As we just mentioned, polar dissolve polar, like dissolve like. It is the same. It is the same basic of the same principle. Now we will go to the two very important theories that explain the adsorption, which is the first one is chemical the Langmuir adsorption theory. This is the most important theory for in chemistry, not in chemistry, in catalysis, because Langmuir discussed the chemical adsorption, and the chemical adsorption is the main idea of heterogeneous catalysis. So please try to focus on this theory because it's very important. Before adding this theory, of course, you know, there is nothing ideal. That means if you just say a rule, any rule, you have to minimize the effect of some factors to be to get it easy for calculations. Now he tried to minimize some factors or neglect some factors. So he added some assumptions. What are the assumptions of Langmuir? Number one, gas form only one layer. So he didn't like to make a headache. Only one layer, to just neglect the other the effect of second layer or third layer. So just to minute the error. That's all. But we can't say it is not formed. It is he assumed that it is only one layer. Next is at a given temperature, a dynamic equilibrium must be attained. Dynamic equilibrium means there is an equilibrium, means there is adsorption and desorption, like this. 1, 2, and 4 are adsorbed, 3 and 5 are not adsorbed. Then equilibrium occurs. Other two, you can see only 2 left the surface, desorbed, and the other 2 was absorbed in the surface. So there is a dynamic equilibrium. Dynamic equilibrium. It is not static equilibrium. Dynamic equilibrium means adsorption occurs and desorption, absorption and desorption, and so on. The third assumption is he assumed that the solid is perfect, homogeneous. And also I assume that it is not true 100%, because there is no perfect surface. There is no perfect surface. Okay, he assumes that the surface is perfectly homogeneous like this. However, he assumed this kinks and edges and all the other things are not there, but it is not completely true. And he also assumes that the interaction between adsorbed molecules is assumed to be negligible. This means these particles are very close to each other, but they don't interact. This means each one of them is alone. He doesn't want to interact or just click, just hit or collide with the others. Just sleep alone. Number 5, the heat of adsorption is therefore independent on coverage. That means delta H is independent on theta. Coverage means the surface, as you can see here, the first one, the surface here, this one, the surface, if the surface is covered completely, this is theta equal 1. And if theta independent on theta, this means whatever the amount of theta or the coverage of theta, the delta H doesn't change. He assumed like this. He assumed this. This is the surface, and these are the molecules. They are adsorbed, and like this. All the surface is similar. All these particles don't interact to each other. All these particles, there are some kind of dynamic equilibrium, and he assumed that all the surface is one unity, and the surface is the covered surface is theta, and the uncovered is 1 minus theta. So it is known that the amount of course, the adsorption process increases when the surface is empty. So if 1 minus theta is large surface, the adsorption process will be higher. If theta increase, the amount of adsorption or the rate of adsorption will be low. We will see this in this slide. The covered surface is theta, and then the uncovered surface is 1 minus theta. The rate of adsorption depends on, is proportional to the pressure of the gas and the surface which is not covered. If the surface is, if the covered surface, if the uncovered surface is large, this means a lot of adsorption will occur. And if the P is great, if P high, this adsorption is higher. Then the rate of adsorption depends on P and 1 minus T. And the rate of desorption, then the rate of adsorption, of course, we will remove proportionality sign and equals K1 P 1 minus T. This is the rate of adsorption. And the rate of desorption is proportional to theta. Then the rate of desorption equals K2 by theta. At dynamic equilibrium, the rate of adsorption is the same as the rate of desorption, like this. The rate of adsorption is the same as rate of desorption. If this is equal this, if K1P 1 minus theta equals K2 theta, then at this time K1P minus K, just make it more simple and more simple, and then more simple. It's the same equation, just multiply and subtract. It's the same. Then finally we get this equation, which is theta equals K1P over K2 plus K1P. Just we also make some kind of rearrangement. We abbreviate it like this. If we assume B equals K1 over K2, this is very easy, no problem. Theta equals B by multiplied by P over 1 plus B multiplied by P. In this equation, I'll just tell you very small thing. If you have million rupees, please pray for me to have million rupees. If you have million rupees and I just give you one rupee, and I tell you, somebody will tell you how much rupees you have. How much will you say? How? What is the number you will say? You will say 1,000,001 or only 1,000,000? You will just say, I have 1,000,000 rupees. Okay, I'll complete. No. And also microphone is working. So I think, yes, I'll continue. Of course, if you have million rupees and you just have one more rupee, then if somebody will ask you how much money do you have, you will simply say, I have million rupees. But now, do you remember? So if P is very small compared to 1, this means this value. Okay, brother? This means this value can be neglected and the theta will be B small, B P. And if P is very large, this means that this theta will equal to, then theta will equal to 1. Okay? Uh, of course, this is this is assumption that theta, if theta equals to V over Vm, theta is the amount, is the covered surface. V is the amount already on the surface of the gas already on the surface. Vm is the monolayer, the amount of gas which can cover monolayer of the surface. Okay, theta equals V over Vm, and we can just substitute instead of theta we add V over Vm, and we can get, this is very simple mathematics. P over V equals 1 over VMV plus P over Vm. As this is the linear form of Langmuir equation. In this equation, we just make a plot between P over V and P. At this time, the slope will be 1 over Vm, and the intercept is 1 over Vmb. Okay, and this is and we can sometimes when you make adsorption process or adsorption experiment, they ask you which is it belongs to Langmuir equation or Friendlich or Tinkin or if it gives straight line, then it follows, or it is due to, or we can apply Langmuir equation on this adsorption process. And of course, the slope is 1 over V, just we mentioned right now, and 1 over VMB is the intercept. Vm means you can see this the amount of the gas, the amount of molecules, the amount of gas, or the amount absorbed, which can cover one monolayer of the surface, all the surface. So, what is the reason? Why can we do like this, or why can we? What will we use this? Simply, if I ask you to calculate the surface area of this material, surface area of this material, now, and I give you the surface area which is covered by one molecule, simply you can say that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 by, for example, 2 centimeters, then this will equal 24 centimeters, right? Right. Here we can use this to calculate the surface area. If we calculate Vm and we just make small calculations, and we will get to know the surface area of this material. And to know surface area is very important to study some many parameters, as we can see in future, inshallah, in another lecture. Of course, in this hole, it has some blocks like this. If you count how many pieces like this, and you know the surface area of each one, you multiply and you can get the surface area of the material. So we can use Langmuir isotherm or Langmuir equation to calculate the surface area of solid materials, like as I'll tell you. If we calculate Vm, this means if we divide to 22.4 liter for 1 mole, then we will get to know the number of moles. And from number of moles, if we multiply by Avogadro's number, we will get to know number of molecules. And if we get number of molecules, if we multiply by sigma, which is the area of one molecule, this is the number of molecules. If we multiply by the surface area of one molecule, then we will get to know the surface area of all the material. And then if we divide by its weight, then we will get to know the specific surface area, I mean for 1 gram. I just wrote it like this. It is very nice. If this is the number of moles, V, which is the amount adsorbed, the volume adsorbed on monolayer, divided by 22/400 gives number of moles. And if this is the number of molecules, if we multiply number of moles by N, which is Avogadro's number, it will give number of molecules. And if we multiply number of molecules with the surface area of one molecule, it will give total surface area. And if we divide by weight of the solid material, it will give specific surface area, which is surface area per 1 gram. And this is this equation. We can simply change N by its value. And the sigma, if we use sigma for nitrogen, it is known as well. We can just add it, and we can use this equation and calculate the surface area of a substance. So from Langmuir, we could calculate the surface area by knowing Vm of the material. And this is a simple example as well. Please read it. The volume of nitrogen gas at 1 atmosphere and 273 K required to cover 1 gram of the silica gel is 0.129 decimeter cube. Do you know what is decimeter cube? Decimeter cube. Calculate the surface area of the gel if each nitrogen molecule occupies an area of 16.2 something meter square. This is the surface area of covered by one molecule of nitrogen. Of course, it's direct substitution, and you can just see it. It's very easy. You divide the number of the volume over 22.4 equals something in moles. Number of moles by Avogadro's number, it will give something of molecule, and the number of molecules it will, by 16.2, which is surface covered by one molecule of nitrogen. It will give total surface area, as we can see. This is another example. This is this example you will meet for sure in your work when you can when he gives you some data and he asks you directly, is it follows Langmuir equation or not? I am sure if you read some papers or if you just go to any lab and make some adsorption, he will ask you this question. The following data were recorded after adsorption of carbon dioxide on 1 gram or charcoal at 25 degrees C. Prove that these data follow Langmuir isotherm and calculate Vm and the surface area of the charcoal. The cross section of area of CO2 is 19 angstrom. of course, 19 angstrom square. P equals gives you different values of P and gives you the volume Vm at different the volume at different P's values. So this is P, this is V, and then to apply Langemeyer, we just divide P over V. It's like this, like in this table, and then plot P against P over V like this. It gives you straight line. The slope is, as you, if you remember, the slope is 1 over, slope is the Vm equals 111 milliliter. At this time, if you know the Vm, you can just apply in the equation just in previous slide. It will, and substitute sigma and the Vm and the mass. The mass is 1 gram, okay? So surface area will be 567 meters square per gram. So first question, he asked you to prove it is follows Langemeyer equation or not. If it gives you straight line like this, which is this one, if it gives you straight line, this means it follows Langemeyer isotherm. If it doesn't give you straight line, then it doesn't follow Langemeyer isotherm, and you just check another equation. And this is Vm, the second demand he asked us, and the last is to calculate surface area, and we did. Is it clear? Any problem? Now this is another example, and another example we will also transfer to you, and you can try by yourself. We just talked about chemical absorption. I'd like to ask you a very simple question. What is the main difference between physical and chemical absorption? Excuse me? Excuse me? It's multi-layer. Multi-layer. I just said there is one big difference between them, and beyond this difference, all the other differences are coming. The main difference between them is the formation of chemical bond, okay? After that, formation of chemical, because the formation of chemical bond means that in the first layer, if it forms chemical bond with the surface, this means the second layer will not find the surface to do, so it will be monolayer. But if it's just condensation, so condensation, another condensation, because there is no bond, it is just condensation. And you can make condensation on the wall or the glass or wood. Condensation will happen, whatever it is. But if you make, if you want to paint, for example, in this color, you can't do it on the wall, but you just do it on the wood. Okay, so the main feature or the main difference between physical absorption and the chemical absorption is the formation of chemical bond. Here in Friendlich, he is talking about physical absorption. Physical absorption means multi-layer, multi-layer, multi-layer. No chemical bond, just multi-layer. And they use and these molecules are contacting to each other, and there is attraction between each other by van der Waals forces, which is very weak forces. That's why the heat of chemical absorption, heat of physical absorption is very small. Let's go to Friendlich. In Friendlich absorption isotherm, it is divided into 3 parts. The first part is at low pressure, and the absorption is going up very quickly because the surface is empty. And the second part, little bit intermediate pressure, which is intermediate rate of absorption. And the third part at high pressure, it is like a plateau, and it doesn't change with increasing the pressure. In these three parts or three regions, we will just tell you that at low pressure, the amount absorbed is depending on the pressure very fast. This may happen in the chemical absorption at the beginning very fast until it covers all the monolayer. And in and the W over M equals K by B. Okay, and at high pressure, very high pressure, you can see it is like a plateau. W over M is proportional to B naught. That means it doesn't depend on pressure. And at intermediate pressure, it is like this, and W over M is proportional to P over P to the power 1 over N. And this, in this region, Friendlich studied his equation. So we will take this equation to make it more, to explain about it, and just try to apply, treat it to get Friendlich equation. W over M is proportional to P over 1 to the power 1 over N. W over M equals K P 1 over N. If you can see, K is constant, of course, proportionality constant. P is the pressure gas absorption, and the N is constant. So K is constant, P is N is constant. N is very important constant because once you know N, and there is a kind of category, N equal has some values, and it determines the nature of the surface. And the W is the mass of gas absorbed, and the M is the absorbent mass. This is Friendlich. If we this is Friendlich equation. Of course, I will show you an example of Friendlich equation. But now, just let me show you what is the most application, or one of the most applications for adsorption process is the chromatography. Chromatography is very important in analysis and in our research work, and also in medical science, and etc. 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 Because what is the main or the simplest idea of chromatography? Simply, it depends on the attraction between solute and the stationary phase of the in chromatography. If you have a column like this, and you add stationary phase like alumina or silica or whatever, and you add different substances, mixture of substances, and you want to separate these substances. What will you do? Just add these substances like this, and add solvent. The solvent will take these materials to separate it. Do you know which force will derive these materials to move or to stop? Which force? The force which is deriving these materials to move or stop is the attraction between these materials and the stationary phase. Let me ask you, which will go faster? Those materials which has attraction, more attraction between stationary phase and these materials will remain, or it will go fast? It will. If attraction is high, this means it will stick and will move very slowly. And if the attraction is small, this means it will. It's like if you visit somebody who you don't like, just hello, bye bye. You don't like him, but if you like him, you want to stay with him sometime. You have a drink, you have a tea, and if he is generous, he will invite you for lunch, and chat, 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 and etc. Okay, so you will stay more. You will stay more. Okay, but if you don't like him, just if attraction is in stationary between stationary phase and these materials is high, This means it will stay sometime. It will move very hard, very slow. But if the attraction is very small, this means it will go very fast. This is chromatography. Of course, this is what I have just mentioned now. Uh, it has many types. Chromatography has many types. Let's if you check this picture, the upper one, which one uh, has low attraction between the stationary phase and these materials? The red one has the least attraction. The yellow, and by this technique we can separate and analyze many of chemical materials, and this is how it works. I don't think it will. We will explain it here. If you have a sample, you just add the sample with on this column, and sample will go. And if you can see this is a mixture of solutes together. This is a mixture of solutes together. Okay. At the beginning, all of them are very close to each other. After that, after adding solvent, they started to separate like this. And adding more solvent, separation increases. And adding more solvent, then separation completed until we can just this one will be drained here, and later the blue one will drained in another batch. And I think this is what I have just mentioned now. The less strongly absorbed compounds will concentrate further down the column in the order of their case of absorption. This is what I just mentioned now. And this is how it looks in laboratory sometimes. It is very compact here, and by time we can separate it. And I think we can say thank you very much. If anybody has any question, I am here. We can discuss about it. Okay, please.
As you said, in chemical adsorption, there is only monolayer formation.
Yes.
Then there is adsorption of oxygen over metal surfaces, forming metal oxides.
Yes.
Layer by layer, it keeps on growing. So, is it an example of multi-layer chemical adsorption?
Did I hear you correctly? That oxygen absorbed on metal oxides in different layers. So what is the problem?
Multi-layer.
Yeah. So it's physical absorption. By the way, physical absorption may be converted to chemical absorption. First, chemical absorption starts basically with as physical absorption. Physical absorption occurs, and later the bond is formed. Once the bond is formed, then you will have chemical absorption. Do you understand? So if you have oxygen as multi-layer, so it's very simple to say that it is physical absorption. What is do you have a proof that it is chemical, and we just call it physical absorption? Once it's multi-layer means it made condensation. And I just mentioned in Langemeyer, the first item in Langemeyer, he says that the gas forms only one layer. I told you it is not completely right like this, but it happens some exceptions, not exceptions. It happens that some molecules may be absorbed as physical absorption. In the same time, there is a chemical absorption. So you can imagine that a part of the surface is physical and another part is chemical. It is not ideal as Langemeyer said. Okay, please. Okay, please. Thank you very much.
One of the problem that we have solved, lossless Clapeyron equation.
Which one?
Lossless Clapeyron equation.
Yes. This. Okay. Just wait. This one. Yes. Yes, please.
Sir, I think this equation has some mistake.
Which one?
ln P1 upon P2. ln P1 upon P2, not ln P1 upon P2.
This one.
Yes, sir. And in one problem, you have solved that the del H value is positive, that is endothermic process, which is not possible in general.
Excuse me, I don't catch you, please.
Okay, sir.
You are talking about this equation.
That equation is actually ln P1 upon P2, not ln P2 by ln P1.
Just wait. This is, if you add ln P1 over P2, this will be here T1 minus T2.
Yes.
That's it.
Yes.
Do you understand?
But in one problem, you have answered that the del H value is positive. In the further,
Delta H?
del H is positive in further slide, in numerical problem.
In here?
Yes, sir.
Uh,
Del H is positive, which is not correct, I think.
yeah, I may have a mistake in the sign here. I'll correct it.
Clausius Clapeyron.
I'll check it again. Okay? Okay. Please, I'm listening.
My query is only for the students, sir. I know.
Okay. Thank you very much.
One more thing here is that.
Yes.
Is there any example of endothermic adsorption?
Endothermic absorption? For me, I didn't hear about it. But it may be there, it may be there. But for me, I didn't hear about it. My knowledge is that this process is exothermic process. If you have an example of endothermic process, please explain. No problem.
As I have studied,
Yes.
that in case of isomerization process, one compound is converted to another compound.
Yes.
The process is reversible, but the interaction between adsorbent and a metal catalyst, adsorbate and adsorbent, that process is very endothermic process, and that's why for the process to carried out, high temperature is required.
Yes.
According to Bent-Off equation.
Thank you very much. Now you give me another information. Thank you.
One thing is this.
Yes.
Second thing is any deuteration process, that is one hydrogen atom is replaced by deuterium.
Yes.
So that process of interconversion is also endothermic process. So these two are the very common examples for
Okay. Thank you very much. Thank you. Our friend just said that there are some examples that makes the adsorption endothermic. Okay. But these examples, of course, there is a rule which may have exceptions. Okay, these are exceptions of the main rule, which is adsorption is exothermic process because the formation of the bond. Okay, this is the main rule. But what my friend just said, it is exception of these rules. Okay, so but for our study, for our level, it is exothermic process. It may have some exceptions, yes, of course. Okay, thank you, brother. Thank you. Okay, thank you very much.